Welcome to MRS Bulletin's Materials News Podcast, providing breakthrough news and interviews with researchers on hot topics in materials research. My name is Sophia Chen. Look around your home. Take the wood in your sofa or the glass in your windows. These conventional materials are useful for their bulk properties and three-dimensional structure. But for emerging technologies such as flexible electronics, such as a tiny sensor implant for monitoring chronic illness, or a foldable smartphone, researchers are developing materials with properties on a smaller, flatter scale. For these applications, they are developing materials made of thin layers, such as graphene. The layers stick together via van der Waals forces. To develop a layered material for a particular application, it's important to measure its mechanical properties, such as how easily it bends and breaks. But layered materials are distinctively complicated to study. Henry Quansah-Offel, a postdoctoral researcher at the University of Illinois at Urbana-Champaign, explains.
Using layered materials are very challenging because you have so many mechanisms that can occur at the same time.
As you apply force to the layered material, it might stretch or crack due to many different mechanisms, such as the layers separating, or atoms rotating, or being pushed to form structures known as kink bands. In new work, Offel's team demonstrate a way to characterize the mechanical properties of layered materials. The technique can elucidate some of the mechanisms behind the material's deformation. They use a particular technique known as nanoindentation.
You are almost like driving a nail into the material and then just getting the mechanical fingerprints of the material. The proverbial nail here is it's a diamond tip. And then the hammer is just just some fixture that we are using to drive some currents to move the diamond tip into the material.
This technique characterizes the material's properties at localized spots on the sample. This is in contrast to conventional mechanical tests, where you compress or stretch a bulk sample. This localized characterization makes nanoindentation an efficient characterization technique.
Compared to the bulk test, is that you don't need to make so many samples to get the mechanical information. You just need one sample and you can run hundreds of tests on them. Because it's very localized, you can get more information about when various deformation events start on the atomic scale.
When you drive a sharp tip into a layered material, it first starts to undergo an elastic deformation. This means that if you stop driving it, the material will revert back to its original shape. But drive that tip in past a certain point, and the material begins to deform permanently in what's known as plastic deformation. Drive it in some more, and it fractures. Offel was interested in the threshold conditions, where the material goes from elastic deformation to plastic deformation to fracture.
Under which conditions will it fracture, right? And does fracture get easier as we increase temperature? So those are some of the questions that we were trying to answer here. And apart from that, we were also looking at how hard the material is.
His team studied a naturally occurring layered material called muscovite as a model material. Muscovite is abundant in Earth's crust.
The reason we chose it instead of a material like, say, graphene is that it's not as expensive. It's very abundant in the Earth's crust, and so easily attainable. It has all of the characteristics representative of other layer materials, but you can acquire them very easily as well.
When they drove the diamond tip into the muscovite, at certain points the tip would go into the material suddenly, which they referred to as a pop-in. When the tip would go in suddenly, more than 5 nanometers, that was a sign of fracture rather than plastic deformation. They also studied how the muscovite's response changed under different temperature conditions.
As we are increasing temperature, the material easily fractures. It's not as resistant to fracturing.
The point of the study was not to study muscovite specifically, but to present a general framework for identifying how layered materials deform and fail in response to stress. Studying the fracturing of layered materials has applications beyond flexible electronics. It's also useful for understanding Earth's crust, which contains layered materials. This type of mechanical information is important in applications such as carbon sequestration or hydraulic fracturing, where fluids are forced into Earth's crust. This work was published in a recent issue of Communications Materials. My name is Sophia Chen from the Materials Research Society. For more news, log onto the MRS Bulletin website at mrsbulletin.org and follow us on X at MRS Bulletin. Don't miss the next episode of MRS Bulletin Materials News. Subscribe now. Thank you for listening.